Starting today with complex and rational zeros of a polynomial. What is a complex number? A plus bi. That's a complex number. What's a rational number? A over b, where b doesn't equal 0. That's a rational number. Okay? And then we have the polynomials. What's a polynomial? Chase? Okay. That's an example of one. A polynomial has non-negative integer exponents, and they have real coefficients usually. And zeros are x-intercepts, x minus c, for instance, where c is a 0. So we're going to find them. The order of the degree of the polynomial tells you how many solutions there are to the polynomial. That's how you know when you're done. Now, these are like mid-range problems. The tough problems won't show up until second semester around March. Okay? That's when you get to the highest level problems of solving. So, with that said, I think we're ready to do a little bit. Let me know when it's about, I don't know what time we get out of here today, since it's all messed up. 16? All right, so let me know when it's about, I don't know, about 10 minutes. Okay? In 10 minutes, let me know when it's time. Okay? And I'll stop it. I think I have it already. I'm very excited about this. Because I was just like, remind me to shut the video off for this too. All right. So, a theorem of a conjugate pair of zeros. That's in case I'm not here. Anyway, the coefficients, if it has real coefficients, and b is not equal to 0, then z hat means that it's a conjugate of a number. For instance, if z is a complex number and it equals 3 plus 2i, z hat is the notation that means it's a conjugate, 3 minus 2i. So the little hat means conjugate. I don't know what other math term to call it. I just call it a little hat. A little line over the z. Z is normally a complex number. Okay, so z hat is the complex conjugate of that. Do you remember Descartes' rule of signs? I know you might not know it, but do you remember how we charted it? We always put what? The positive roots, the negative roots, and what was the last column? Yeah, non-real complex roots. And I said this number in the last column always had to do what? Be even or 0. So you always had to have a 0, a 2, a 4, and a 6 in this column. And that's why. Because if 3 plus 2i is going to be a 0 of a polynomial, the conjugate, 3 minus 2i, is also going to be a 0 of the polynomial. You can't have one without the other. Do you know where that comes from? Why you have to have conjugate pairs? Yeah, I is the square root of negative 1. Yeah, equals I. And from the quadratic equation, don't you have b squared plus or minus the square root, the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a? Well, that's where it comes from, the plus or minus part. That's why you have to have 2 of them. Every quadratic has to have 2 solutions. If there's an imaginary, there's going to be a positive and imaginary. So that's the complex number. That's why you write a complex number as a plus or minus bi. It comes from the quadratic equation. Nice. So they always come in pairs. So in Descartes' rule of signs, you have 0, 2, 4, 6, 8, things like that. Okay? Double roots count as 2 also. Don't forget that where it's tangent. It counts for that also. All right. I didn't even check to see if this was on. Let's move on. I like the little hat symbol, though. It's pretty cool. All right. A polynomial with real coefficients and a leading coefficient of 1. Put this in terms that, what does it mean, a leading coefficient of 1? Yeah, a equals 1. The proverbial a in front of the function equals 1. That's nice. That saves us a step. So express f of x as a product of linear and quadratic polynomials with real coefficients that are irreducible. Look at all these college words. I love this. Look at all this stuff. Sam's getting excited, I can tell. Given zeros in the degree. So your answer has to have degree 2. How would you write it? First of all, how would you write this as a factor? Huh? Well, now how do you write as a factor? X minus negative 4 plus 3i, right? That's a factor. And x minus negative 4 minus 3i is the other factor, correct? Well, it wants it written as a product of linear and quadratic polynomials. So that's a linear factor. I can't leave my answer like that because you have to have real coefficients, so that means I'm going to have to multiply this out. And they said that a was 1, so that's good. So this equals f of x. When I multiply this out, it's going to have degree 2. When I multiply it out, what should happen to the i's? They'll turn into real numbers, correct? Good. Well, let's just see if this is true. F of x, and you're going to see something really cool, I think. At least I hope you do. Are you ready? 2 things really cool today. It's great to be a Spartan in 5th hour class today. X squared. Minus. I do this kind of slowly because there's so much going on. Some of you just like, that's fine. But some of you, I don't know, just bear with me for a while. X times negative 4 minus 3i. Minus x times negative 4 plus 3i. There we go. Plus negative 4 plus 3i times negative 4 minus 3i. Okay? I know it is. Good thing you know what you're doing. So yeah, I fooled it all out. And then I took, that multiplied and that. So finally I have f of x equals x squared. You guys can probably do this in a lot faster steps than I can, but I always like to make sure I don't make mistakes. So it's plus 4x plus 3ix. All I'm doing is getting rid of the parentheses so I can combine like terms. Plus 4x minus 3ix. Let's see, negative 4 times negative 4 is 16. I don't have to worry about multiplying out the middle, do I, because it's a conjugate? Then finally, when I multiply out the end, 3i minus 3i, when I multiply it, there's going to be negative 9i squared. Yeah, which equals a positive 9. Now I think I'm ready to combine things. F of x equals x squared. Booyah, got it. Any other x squareds? No. 4x, any other 4x's? There's another one right here. And these are opposites, so they go away. So that gives me plus 8x, correct? Plus 8x. And then I have 16 plus 9. So that gives me 25. How in the world do you tell if you're right on this? Plug what? Yeah, plug it in the quadratic equation, except, well, how do you have to change your equation? What do you have to be in? You have to be in, oh, I just closed it. Oh, well, I'll find it back really quick. Yeah, you have to make sure you're in A plus BI mode. I thought I hit my calculator. There we go. Okay. Second quit. Large screen mode. A plus BI. Enter. Second quit. Program. I think yours was a quad P. And what was the equation? 8? Or 1, 8, and 25. Okay, got it. 1, 8, and 25. I think that's nifty. Negative 4 plus 3i, negative 4 minus 3i. Do exactly what you're supposed to be doing. Obviously, if you have more, you can have it into the degree of 2. But this is a polynomial, so we're in good shape. All right. All right. Let's see. Moving on. Let's see what's next, shall we? Oh! Degree 4. Wait a minute. This can't be right. A polynomial with real coefficients and leading coefficient 1 has the given zeros in degree. That has to be degree 5. Is there a miss?
I know, but there's always minus sign, so that's 1.
Oh, so this isn't here.
No, it is there. It's there.
You guys are judging without thinking.
0, 2, -2, and then it's -2 minus 1. Oh,
Why? Because the fourth root has to be -2 plus I. Yes. I knew one of them had to be marked out. All right, so now we can do this with the factors. So x, that's pretty nice and nifty. And then we have x minus 2, that's nice and nifty again. Then we have x minus a -2 minus I. And x minus a -2 plus I. Okay? And then we multiply it out, and we get to where we need to be. Now, I don't have to multiply out. These are fine. I don't have to multiply those out. I don't have to have a degree 4 polynomial. It says you can have it with linear and quadratic polynomials with real coefficients. These two are fine. The only thing I have to multiply out are these two. Okay? So you're trying to get it all factored. You're not trying to get the actual polynomial. You just want it factored, and we don't factor using imaginary numbers. We use those to give us our answers. So, f of x, and we know it's going to have a 1 out in front because it said so, x minus 2, and I'm going to use my fort here to do some multiplying. Yeah, so it's going to be x squared minus x times -2 plus I. There's other ways you can do this, but I do it this way. Why? I don't know, but I just do. Plus -2 minus I, -2 plus I. Okay? And usually I'm ready to clean house pretty quick when it comes to the final answer. I'll keep the fork because I don't think I'm quite ready yet. X squared plus 2x minus xi plus 2x plus xi plus 4 minus I squared. Does that look right? Okay. So then f of x equals x times x minus 2 times x squared plus 4x. The xi's cross. You got the 4x right here. And then the I squared is -1. So it'll be plus 5. And you'd be surprised how many people factor x squared plus 4x plus 5. It can be factored. Even after doing this, I can factor that. No, you can't. You can't factor it over the real numbers. Well, sure, you can factor over the imaginary numbers because that's where we started. Oh, yeah, but what about plus 4 plus 1? Well, yeah, that multiplies to 4, not 5, and it doesn't add up to, you got it backwards. So anyway, that's a common mistake whenever that's given as a polynomial to factor. Okay? So far, so good? Fantastic. How far are we? To 10?
That's good enough.
Excellent. All right, we'll do this. We'll do one more problem, and then we'll get to the little thing I have planned. Okay? Anyway, the theorem of rational zeros of a polynomial. Every polynomial has a leading coefficient, and every polynomial has a constant. If it does have a rational zero, this is a short way of writing it. F of x equals ax to the n plus ... plus c at the end, some constant. If it has a rational number that makes it equal to 0, It has to be the factors, all the factors of the constant, divided by the factors of the leading coefficient. Life is good when A is 1. When A is 6, that means you could have plus or minus 1, 2, 3, or 6 in the denominator. Then all the factors of C in the numerator. Okay? So if you had the equation 2x squared plus 3x minus 5, I know by looking at that the answer is not going to be 7. I know by looking at the answer is not going to be 4. I know by looking at the answer is not going to be 3. I know by looking at the answer is not going to be 105. The answer is if it's a rational number, not real, rational. If it's a rational number, it's all the factors of the constant, 5 and 1, over the factors of the leading coefficient, 2 and 1. The only possible rational factors could be 5, 1, 5 halves, or 1 half, all these combinations. 3 halves would not work. If you come up with the answer, I got 3 halves, I can say you're wrong just by looking at it. That can't be right. Okay? So, you throw Descartes' rule of signs in here, you know one of the answers is going to be positive. Is it rational? Not necessarily. Descartes' rule of signs works for real numbers. This just works for rational numbers. The difference, of course, is you can write 1 as a fraction. You can write 1 using square roots. Because the factor theorem says you have to include the negative factors as well as positive factors. For instance, the factors of 36, you were all taught was like 1, 2, 3, 4, 9, 12, and 36. Well, actually, the positive and negatives, because negative 2 times negative 18 is also 36. Okay? 18.
Is that the positive and negative for all 4 of those numbers?
Yeah, but if I put the positive and negative down here also, that's kind of redundant because they can be the positive or the negative. I don't need it in both places. So usually I just put it out in front, positive and negative. Okay? So I know the answer can't be 192. All right. So that's kind of nifty. So the equation has no rational roots. What are the possible rational roots for this? Well, plus or minus 7 and 1 are the factors of the constant. And the factors of the leading coefficient are 2 and 1. How do you know if any one of those combinations, which I just leave it like that because I know I'm talking about, it can either be plus or minus 7, plus or minus 1, plus or minus 7 halves, or plus or minus 1 half. You take all the combinations. How do you tell if something has a rational root? Best of the brightest right here. Time to prove it. Time to shine. Synthetic division would be nice, but not quite as efficient. What's true about synthetic division if it is a 0? What equals 0? The remainder. The remainder is also a fancy name for the function value. So all you have to do is put each one of those in. If it comes out to equaling 0, it is. If it comes out equaling not 0, it's not. Sure, you can do synthetic division, or you can lock and load and just put those numbers in and see if it works. Yeah, that means take the calculator out, get it ready, load it up, and move on. Now here's a fancy way of doing it. I'm going to show you a fancy way. Y equals, I'm sure you probably already know this, I'm just reviewing it. 2x caret 5, 2x caret 5 plus 3x caret 3 plus 7. It is, I'll get it fixed. Delete. 2x to the 5th plus 3x cubed plus 7. All right, got that? Oh, there we go. Plus 3x cubed plus 7. Are you ready? All right. So I'm going to go to second and table set, which is right up there. Right above window, I believe. It says table set. Table start I really don't care about. In calculus it matters, but here it doesn't. And I want my table set up on ask for the independent and dependent I want auto. That means I'm going to type in an x value and it gives me the corresponding y value. Okay, does that make sense? All right, so now I'm going to go to second and table. Okay, those numbers aren't for my equation. So I'm going to type in 7. I got 34,650. The next option is -7. That doesn't work. What kind of function is it, though? Negative x equals the opposite of regular x. So what type of function is it? It might be an odd one. Oh, no, it's not exactly equal. Darn, I was all excited. Okay, never mind. Moving on. Checking out 1, doesn't work. -1, doesn't work. 7/2. Doesn't work. -7/2. Nope, doesn't work. 1/2. Nope, doesn't work. What about -1/2? Nope, doesn't work. Heh, -1/2. There, it doesn't work. None of them work. Therefore, that has no rational root. Could it still have a real root? Absolutely. But it doesn't have a rational root because none of those equal 0. And that would be your work. There. None of the roots equal 0. Huh? Oh, you just say none have function value equals 0. You don't have to list them all. Just none of them have a function value equals 0. Therefore, there's no rational roots. No rat roots. Roots. That's a big phrase I used to use all the time. Rat. All right.
So if we want to do this, like again, we just put in the equation for y equals and go to table.
Yeah, and you start typing in your numbers. You can also do auto fill, but then you're scrolling around. This way, you just type in what you want, see what you want, move on. Okay? Fantastic. Let's see what the next one is. 13, I get out? Oh, we'll start here tomorrow. How far is this? 13? So try to get to 13. Yeah, tomorrow, and here's Monday. All right, so try to get there tomorrow. What page is this? Page 247. All right, instead of a brain break, we're going to do something a little different. I just assumed, oh, and if you're listening to this, I'm going to shut you off.